Hey everybody. Uh, this video is going to cover section 6.3 and 6.4 in the textbook, and that is going to be about sampling distributions and the central limit theorem. So in section 6.3 there are just a couple things I really want to highlight, and that's a couple definitions. One of them is this definition parameters, and the other is the word statistics. So basically they both describe kind of the same thing. Like for instance, the mean could be a parameter or it could be a statistic. Basically, a parameter is just something that comes from a population, and a statistic is something that comes from a sample. So that's really important to know, and I'm going to kind of refer to those words parameters and statistics in different situations, and you really should know what I am talking about. So as we get into chapters 6 and 7 and 8, I'm going to be using these words a lot, so it is important that you are familiar with what those mean. So we want to talk about what statistics are good estimators of parameters. Actually, we're not even going to talk about that so much. This section, noted in this bullet point right here, says here we prepare for some theoretical heavy lifting to come along in the next section. You know, I'm going to skip over that stuff actually, and let's just get into the next section, which is all about more about sampling distributions and also the central limit theorem. I guess with all this heavy lifting, what we're going to see in the central limit theorem are these two important observations. And I guess I should talk about the important terminology first, shouldn't I? So the important terminology is something called the sampling distribution of the mean. This is a collection of sample means that come from a population. And you know what, we're actually going to get into this later, so let me just skip right over into section 6.4. So 6.4 is all about what's called the central limit theorem. So let's do a little preliminary example which will kind of give us an idea of where this is coming from. This is going to be kind of similar to the problem at the end of the group work in section 6.2. So the good people at Fizzy Pop claim the mean volume of soda in all 12-ounce cans of soda is 12 ounces. Right? You'd expect that. It's a 12-ounce can of soda with a standard deviation of 0.5 ounces. If you select one can of soda and it contains 11.85 ounces, you probably wouldn't find that too unusual, right? I mean, it's not going to be exactly 12.00 ounces in every can. It's about that. You know, the machines are prone to a little bit of error. So, you know, maybe you have a little less, maybe a little more. You've all opened up a bag of chips probably and felt like you got screwed and didn't get, you know, as many chips as as other times, or maybe that's just me. So you might not find that too unusual if you opened up a can of soda, measured it, and only found 11.85 ounces in there. However, if you selected 100 cans of soda, and then the mean of those 100 cans was 11.85 ounces, you might consider that a little bit more unusual, wouldn't you? You might think, wait a second, is this company really, why are they advertising that these are 12-ounce cans of sodas? They're really, like, not intending to put 12 ounces in here. 100 cans having 11.85 ounces, that's a little bit more strange. So how much more unusual would you consider this? And that's what the central limit theorem allows us to investigate, this idea of talking about sample means and analyzing data values of sample means. Okay, so what we're going to do is imagine the following scenario. Suppose you have a parent population with a mean mu and a standard deviation of sigma. So a parent population is just like some collection of raw data. Okay, let's say like for the Fizzy Pop, that would be basically like every can of soda they've ever filled. That's the parent population. Now suppose you take a sample size of n, so that would be like in this Fizzy Pop thing like 100 cans, and then you calculate the mean, the sample mean, which in this case was 11.25. So what you want to do is do this again and again until you have taken every possible sample of size n from the population. This is very theoretical, okay? You would never do this. You're going to take a look at that whole population and take like every possible sample of size 100 from that population. And what you have now is a collection of sample means. Okay, you have a collection of sample means. So these sample means are all now your new data values. So your new data values of a new data set. And this new data set is called the sampling distribution of the mean. Okay, it's a new distribution of data values, and we call it the sampling distribution of the mean. And basically what the data values in here are all these x bars of these samples from this sample size of 100. Okay, and here, now that's kind of like the background of the central limit theorem, and here in this box are basically the two big statements of the central limit theorem. And they basically say that the mean of these sample means over here, you guys can see those highlighted, which was accidental, but whatever. Those sample means over here, the mean of them is actually going to turn out to be the population mean. And if you think about that, that may make sense to you. But that, anyways, that's a fact. And what's going to turn out to be about the standard deviation is the standard deviation of these sample means is going to turn out to be much smaller than the standard deviation of the parent population. As a matter of fact, what the new standard deviation of this new data set is going to be the standard deviation of the parent population divided by the square root of the sample size. So those are two very important results, and we're going to be using those going forward for when we consider examples of these sampling distributions. And if you're not really clear on what that means just yet, I think it will become more clear throughout the lesson. And another interesting fact about the central limit theorem is that the sampling distribution of the mean turns out to be approximately normal itself, as long as a couple things are true, one of them being that the parent population itself was approximately normally distributed. And the other thing could be is even if the parent population wasn't normally distributed, if your sample size n is greater than or equal to 30, it turns out this new distribution happens to be normally distributed. And I forget if that, I'm sure that's going to come later in the notes. I don't recall off the top of my head. So in practice, what we could do is if the sample size is sufficiently large, which turns out to be n greater than or equal to 30, you don't need the parent population to be necessarily normally distributed. But it is nice. Or actually, this fact is nice. So the mean of all sample means equals the population mean. We stated that before. And then we also stated that the standard deviation of the sample means is not equal to the population standard deviation. And the author says this is the tricky part. The standard deviation of the sample means turns out to be the parent population standard deviation divided by the square root of the sample size. Okay, so we had our normal z-score formula that looks something like this, right? Some data value minus the mean over the standard deviation. Now this looks a little bit different because our data values are now sample means, right? So this x bar is a sample mean, which really in our kind of work, and what we're going to be using it for is more like a data value. And then mu is the population mean. And then instead of dividing by sigma, we got to divide by kind of our new standard deviation, which is sigma over root n. Okay, so let's do some examples. So we have this example with FizzyPop right here. And the good people at FizzyPop claim the mean amount of soda in all 12-ounce cans of soda is 12 ounces, with a standard deviation of 0.5 ounces. Assuming FizzyPop's claim is true, and the population is normally distributed, what is the probability of randomly selecting one can of soda containing 11.85 or fewer fluid ounces? So we're trying to find the probability of getting a data value less than or equal to 11.85. So what we want to do is convert this variable into a z-score and then find the probability of something less than that by using our z-table. So you can see this graph drawn here by the author. Very nice curve. He must have used technology to do that because clearly this looks a little bit better than mine by hand, and nobody can just draw one better than me by hand. So only technology can do that. So what we want to do is find the z-score for this 11.85, and you'll see the author does that right over here by using the z-score formula, right? Z equals x minus mu over sigma. So 11.85 minus 12 divided by 0.5, and you get a z-score of negative 0.3. So you'll see he has this little scale underneath with his z-scores. So we want to find the probability of getting something less than a negative 0.3. You go back and look that up in the table, and we are in fact looking for the left of that, so that's just going to be the value in the table, which turns out to be 0.3821. Okay, cool. And that's basically like what we've been doing in class the last couple times, just finding the area to the left of z-scores. Okay, so you would not find it to be that unusual. There's a 38% chance that that could happen. Now let's go on to example B. So if Fizzypop's claim is true, what is the probability of getting a sample of 100 cans with a mean of 11.85 or fewer fluid ounces? So in this case, we're trying to find the probability that this sample mean is less than or equal to 11.85. So we're trying to find the probability for a sample mean in a sampling distribution. And when that's the case, we have to use the central limit theorem, which we learned on the last page. And the central limit theorem, really the only big difference here, the only really big difference, maybe even take this down, is that our new sigma, which we'll call sigma sub x bar, is equal to the old sigma divided by the square root of n. That's really the only big difference here with central limit theorem. And you use this whenever you're working with sample means, and like when your new data value is a sample mean, like it is here, a sample of 100 cans. Okay? So what's our data value? Our data value is that 11.85, so that goes right here. We're going to subtract the population mean, which was 12, and then we're going to divide it by our new standard deviation, which is sigma over root n. So we're going to divide it by 0.5 divided by square root n, which is square root 100. Okay? So you do this, and be very careful with your order of operations. Here's a little tip. Put the numerator in parentheses. If you don't do that, and just try to type all of this straight into your calculator, it's only going to divide the 12 by the denominator. It won't divide the whole top by the denominator. So please, that's a really good tip. So try to do that, and try it right now in your calculator. You can pause the video, and you'll see that z ends up equaling -3 if you input that correctly. If you don't get that, then make sure you put those parentheses in there. So now what we have is a z-score of -3. So what's the probability of getting a value less than -3? Well, we'd look that up in the table, and we get this really, really small value here of 0.0013. So just like you may have suspected, that would be really unusual to get a sample of 100 cans that have a mean of 11.85 or fewer fluid ounces. Okay, and here's a little summary right over here. So what's the difference? The only practical difference in calculating these probabilities is that if there's only one selection, then you're doing it kind of how we did in class on Tuesday. If there's a sample size, a sample mean you're looking at of size n, then basically the only really big difference is this sigma gets replaced with sigma over root n. That's really the only difference. Okay, cool. So your turn. Why don't you try this example, pause the video, give it a try, and then once you press play, I will go through it, and you can see if your answer matches up with mine. All right, cool, let's go for it. Calculate the probability that a random selection of 10 adults has a mean weight greater than 210 pounds. All right, so first thing I'm going to do is draw my curve. And actually, the first thing I probably should have done is read the whole problem. Oh boy. Oh boy. Wow, even with a mouse for a hand, I still draw a pretty darn good curve. Okay, your turn one. An elevator states that there's a 2,100 pound weight limit, or 10 people. Assume the weights of adults are normally distributed with a mean of 165 pounds and a standard deviation of 35 pounds. I'm going to underline those words. That's for my parent population. And the weights of adult men are normally distributed with a mean of 161 pounds and a standard deviation of 28. So now they're just talking about men, not all adults. We want to find the probability that a full elevator will exceed the stated weight limit. So this will happen if the mean weight of the 10 people is greater than 210 pounds, right? Because 10 times 210 would give you this 2,100 figure, which is the weight limit. Okay, so calculate the probability that a random selection of 10 adults has a mean weight greater than 210 pounds. So I know my mu of 165. This is my mean of 165. Cool. And I've got to mark 210 on here. Where is 210? Well, it's definitely over here to the right somewhere, right? That always happens. Cool. And we're trying to find the probability that a selection has a mean weight greater than 210 pounds. So where am I going to shade? I'm definitely going to shade to the right, greater than this data value. I know I have there's no chance I'm able to shade this in. Oh, there we go. Okay, cool. Awesome. So what we need to do is find the z-score for this 210. So the z-score is going to be x minus mu over sigma. But the problem is that we're doing for a random selection of 10 adults. So that's where the central limit theorem comes into play, because we have a sample mean we're looking at. So it's going to be x, technically it should be x bar, because it's talking about a mean weight, a sample mean of 210, minus mu over sigma over root n. Cool. So let's calculate this baby. X bar is 210. The mean is 165. Divided by the standard deviation, which is 35. What the heck? 35 over square root of 10. Cool. So then we're going to punch this all into our calculator. And let me get a calculator up to do this. 210. Oh, I want to put that all in parentheses. 210 minus 165 divided by 35 over square root of 10. I'm working with a really bad calculator here. Give me a break. And I got 4.065. So I would round this up to 4.07, right? Cool. So round that up to 4.07, and so that's my z-score here. So z equals 4.07. So I want to find the probability of getting something greater than 4.07. So let's look that up in the table. Little bit of a problem. We don't go up to 4.07. But we have this note that says for z-scores of 3.5 or higher, use an area of 0.9999. Alright, so I guess we're going to use that one then. So that means this area right here to the left of this equals 0.9999. So the probability to the right of this, which is what we're after, is a probability of 0.0001. So that is the probability of this shaded region over here. Okay? Cool. All right, let's move on to the second example. Calculate the probability that a random selection of 10 adult men has a mean weight greater than 210. So now we're working with 10 adult men, not just random 10 adults. So let's draw our curve again. Yeah, not the best I've ever drawn. So now our mean is what? It is 191 pounds. And again, we're still trying to find the probability that it's greater than 210. Okay, so what we need to do again is our z-score. And also we're trying to find the probability that it's greater than this, so we're trying to shade to the right. That's the region that's greater, correct? Yeah, of course it is. So, we're going to find the z-score, which is 210 minus 191 divided by the standard deviation. What's the standard deviation of men? 28 divided by square root of our n, which is 10. Cool. So, again, we want to put this into our calculator. 210 minus 191 divided by 28 divided by square root of 10. And I am getting for an answer 2.14 or 145, which we would want to round that to 2.15. All right. So that's our z-score. And now we're going to use that. That's our z-score for 210 pounds for adult men. And now we want to find what's the probability of getting something greater than that. Well, we're going to use our table, which is going to give us the area to the left of that. So let's go ahead and look that up. So we're looking at 2.15, 2.15. So that's 0.9842. 0.9842. So that's 0.9842. So what is that going to give us for a probability for the area that we're actually concerned about, this area over the right? What are we going to do? It's going to equal 1 minus 0.9842. And that will come out to be 0.0158. So that right there is the final answer. The probability is 0.0158. So does the maximum number of people seem appropriate? Well, if you just assume that it's going to be 10 random adults on the elevator, then yeah, that seems appropriate. You're only going to exceed the weight limit very, very rarely, 1 out of 10,000 times. But if you have 10 adult men on the elevator together, you're in trouble about 1.5% of the time. That's kind of a lot. So that could definitely be a problem. Now let's think about it. Is it going to be likely that you're going to have 10 adult men all getting on the elevator together? Yeah, that doesn't seem too unreasonable to me, right? Maybe like a sports team or something like that. There are definitely situations where you could have 10 adult men together, a bachelor party, that all get onto an elevator together. So does the maximum number of people seem appropriate? I would say probably not, because if those 10 people are all men, you could be in trouble here. 1.5% of the time, you're going to go over that weight limit. So that could be a problem. All right, why don't you try this second your turn? I'll pause the video and let you try it, and then when you resume, we'll see if your answer matches mine. Okay, so this, your turn, says later in the course we'll conduct hypothesis tests where we use sample data to test a claim about a population. This is really the essence of statistics and statistical research, is doing these things called hypothesis tests, which we'll learn about in Chapter 8. So suppose I breed and sell beef cattle. I claim that my cows' weights, when fully mature, are normally distributed with a mean of 140 pounds and a standard deviation of 250 pounds. So, if you bought one cow and it only weighed 1,350 pounds, you wouldn't think anything fishy is going on, right? This is definitely, they're not all going to weigh 1,400 pounds. But what if you bought 50 of my cows and the mean weight of all those cows was only 1,300 pounds? Would you think that that was just kind of bad luck? Or would you think that maybe there was something fishy going on with this farmer, and maybe the true mean weight is not 1,400 pounds, but is actually closer to 1,300 pounds? And that's what we're really getting at analyzing. So let's assume my claim is true. Calculate the probability of getting a random sample of 50 cows with a mean weight of 1,300 pounds or less. So what we're going to do is draw a normal curve. Oh, that's a nice looking curve. And so what is the mean? We're going to assume the claim is true. So the claim is that the mean is 1,400 pounds. That is our mean. And we're trying to find the probability of getting a mean weight of 1,300 or less. So this is about where 1,300 would be, right? We're trying to find the probability of getting 1,300 or less. So I'm shading to the left. All right, cool. So let's go ahead and do it. What we want to do is we want to find the z-score. That way we can find what the probability is of this area. So z equals, our value here is 1,300. And we're going to subtract the population mean, which is 1,400, and divide that by sigma over root n. Our sigma is 250 divided by the square root of n, and our n is a sample of 50 cows. Oh boy. Cool. So we punch these all into our calculator machines, and let's see what this spits out. 1,300 minus 1,400 divided by 250 divided by square root of 50. I'm getting negative 2.828. So we would round that to 2.83, negative 2.83. All right, so now we want to look up that value in our table and find out what the probability is to the left of negative 2.83, which will be given to us. Negative 2.83, negative 2.83 is right here, so 0.99. Oh, I'm in the positive z-score page. I gotta go negative. Negative 2.83 is over here. 0.0023. So 0.0023. So the probability of this happening by chance, getting a sample of 50 cows that have a mean weight of 1,300 pounds or less, is only 0.0023. That is a really small probability. That's highly improbable. So, does this evidence prove that I am a liar? Yeah. Kind of. Right? And that's basically what inferential statistics is all about as we get into hypothesis tests. This is what statisticians and researchers do. They basically do things like this with this normal curve, and they conduct samples, and they find how improbable this probability is. If this probability is really low, then we say, yeah, then you were probably lying. It's very highly improbable for that to just happen by chance. And this probability is kind of something we're going to kind of, play around with. Like, what is, a really low probability that we would say, okay, you're a liar? I don't know. Is like 0.1 going to be a low enough probability? Probably not. What about 0.01? Yeah, maybe. So generally in statistics, we consider 0.05 to be that threshold. If you're under 0.05, we kind of say, yeah, you're probably a liar. That's really improbable. Or if it's 0.05 or higher, we say, that's not strong enough evidence to prove that. So here are just a very few really kind of technical things to wrap up. We're not going to worry about the details of the central limit theorem. Let's go down here to the convention for minimum sample size. This is actually important. So how do we know whether we can use these z-score methods on sampling distributions? Well, there are two things that just one of these two things must happen, not both of them, just one. One, if the original population is normally distributed, then you're fine. Okay, you can use this method of just using z-scores and the table in the back of the book. Now, if the original population is not normally distributed, then we need the sample size to be 30 or more. And if that's the case, so if n is greater than or equal to 30, then even if your original population is not normally distributed, we can still use the methods that we'd used in this video. Okay? And here are some examples when the central limit theorem applies. So, suppose the population was normally distributed. Oh, right off the bat, normally distributed, that means you can use the central limit theorem. Okay? And when I say can you use it, I'm really answering this question. Will the sampling distribution of the mean be normally distributed? Okay. What about the second one? Suppose the population was not normally distributed. And n equals 64. Well, if n equals 64, that means n is greater than or equal to 30. So yes, we can still use the normal distribution methods. And the third one. Suppose the population was not normally distributed and n only equaled 16, then no, we cannot use this method because n was not bigger than or equal to 30 and the parent population is not normally distributed. Alright, so that's it for this video, and I will see you guys in class tomorrow.